I'm going to start the recording now, and we'll go ahead and get started. Is there anyone here who did not receive the slides via email already? They were sent about 10 minutes ago. Good. All right. You can always just drop your email in the chat if you didn't, and I'll forward them on. While I start to sharing my screen, it'd be great to hear from everyone. If you want to put your name and affiliation with CSDE or the UW if you're at UW, wherever you're from, in the chat for everyone to see. I think that'd be really nice. And I'll introduce myself real quick. I'm Jessica Godwin. I'm a research scientist at CSDE. I'm a statistical demographer with a PhD in statistics from UW. I'm also, some of my time at CSDE is focused on our training, running our training program. We have a certificate program. My statistical and demographic specialties are in survey statistics, Bayesian statistics, small area estimation, child mortality, and housing data to some degree. So without further ado, if y'all want to introduce yourselves in the chat, I'll go ahead and share my screen. Can everyone see this screen right here, the slides?
Yes.
Thank you. Brave person. Wonderful to see all of you from all over campus and even from outside the UW. That's great. One of my, Liz, we don't really get people from your side of campus very often, but one of my dearest friends is a research scientist in nephrology, which I assume is somewhat related.
I wouldn't know, but that's very exciting.
Yeah. All right. Let's go ahead and get started with survey methods. So I want to first put this in full screen. Highlight some resources and materials that this lecture is based on. And then I'm going to talk about a little bit about why survey statistics is a thing. Why is it different from other frequentist statistics that you may have learned in other courses or in your research experience. We're going to talk about some typical survey designs, how we do estimation of statistical parameters or population parameters with survey data, and then talk about some ways, some special things one needs to do to visualize survey data properly. And then we're going to talk a little bit about the end, or at the end, about the things that we didn't talk about. So just a few topics that may be of interest to you. I want to say that this is all based in R and on the survey package. Currently, sorry, I'm reading where you're all from, and I just got distracted. One more. How exciting, all over. Okay, so there are two survey packages that you might use in R. One is called the survey package. One is SRVYR, survey R, I believe. It is really a wrapper for everything in the survey package. And I think some things about the survey package are a bit more intuitive and line up more with the statistical motivations behind why we do certain things in the package. But if you are more of a tidyverse fan, the Survey R package is designed to work well with the tidyverse, with Tibbles, and in a pipe-based flow. So all of the principles we talk about here would be the same, but some of the code would be slightly different. So everything that we're going to talk about today is in this survey package. If you have your R open on your machine, go ahead and install this package if you haven't done so already or you don't have it installed. And you can do so by running this line of code. Oh no, there's supposed to be a picture of a textbook here, but Thomas Lumley is the author of the survey package. He's also the author of the survey commands, the SVY commands in Stata, and I think is a contributing author, if not the author of the survey R package I mentioned that is more tidyverse and kind of a little bit more user-friendly, but is really under the hood using the functions we're going to talk about today. And then he also published a textbook called Complex Surveys, a guide to analysis using R. It's really great. It motivates all of the statistical knowledge and really goes into that, and then accompanies it with the actual R code using the survey package. And also, just of note, Thomas Lumley used to be faculty here at UW in the biostat department. There's also supposed to be a nice little picture here. I don't know where that went, but when I want to read about the intuition behind a lot of things in survey statistics, I always revisit lore. This sampling design and analysis textbook. It's really nice. Each chapter introduces kind of a new type of estimation or a new reason for estimation. And at the end of the chapter, there's a really nice summary of like the pros and cons of the methods that are introduced or the contributions and limitations, however you want to think about that. Sarndal, for those of you who are gonna like really interested in getting in the weeds, this is a heavily mathematical book with a lot of analytical calculations and approximations for variance estimators under different types of survey estimation. It's a beast to wrestle with, and I would avoid it unless you really need to. And there might be some of you who would need to one day. If you're at UW and you are a grad student, I would really encourage you to take CSSS Stat 529. If you really know you're going to need survey data, or if you think you want to really dig into some of these topics, learn more deeply about them. It's usually taught by either Elena Arasheva or John Wakefield, and I think it's offered every 2 years in the spring. So I would check into that if it's something that you're really going to need to know beyond this workshop. Okay. All right. So why survey statistics? I'm going to motivate this with a little bit of an example. If our outcome is binary, in statistics or in the known and named distributions of probability theory, we might represent a binary outcome as if our data arose from flipping a coin. This would be a Bernoulli random variable. Or as if we were drawing some number of objects or individuals of a certain type from an urn with 2 types of items in it, right? This might be drawing, red marbles out of a bucket with red and blue marbles. Okay, hold on one second. My dogs are crying. I'm going to let them out real quick so they don't disrupt us further. It's one of my dog's first snows, and she really just can't get over it. Okay, so the 2 options we have, as I said, in terms of probability, like random variables whose distribution has a name, we know everything about them. These are sort of our 2 options. One would be a Bernoulli random variable, and the other one would be a hypergeometric random variable. The difference between these 2 is really an assumption about the experiment that we're observing. So when we think about random variables in math or in probability, we are summarizing some outcomes of an experiment. In the simplest case, our experiment is flipping a coin. But in general, in the statistical sense, an experiment is something that has yet to be done, that will be observed, whose outcomes are unknown until we observe them. So flipping a coin, we know what the possible outcomes are, right? But we don't know until we flip the coin how many heads or tails we're going to get. Same thing with drawing marbles from an urn. We might know that there's 30 red marbles and 70 blue marbles in a marble with 100, or a bucket with 100 marbles. But until we draw 25 of them, we don't know how many of each color are going to end up in our sample, right? So that would be the experiment in drawing from an urn. So in surveys, I guess before we move on to the next bullet, the other thing I'd like to point out is that is a distinction between these two experiments, in that one of these experiments, flipping a coin, can be carried out an infinite number of times. Drawing a single marble from an urn of 100 marbles and not replacing it is an experiment that can only be done 100 times, right? So those are kind of two philosophically different ideas about the experiment that gives rise to a binary outcome. In surveys with human respondents, these binary outcomes we're often interested in are things like disease indicators. Do you have said disease? Or maybe it's some demographic marker, or maybe it is something continuous like income. But it turns out that in a survey statistics context, in this drawing from an urn context, which is what a survey is, it is more akin to drawing from an urn than flipping from a coin, because there are a finite number of people in our population we could survey, right? So if we were to carry out a survey in this finite population sense, sorry, I totally lost my train of thought. I don't know why. Okay, flipping a coin is this infinitely repeatable experiment. Drawing from an urn is not. Oh, I was saying, even if we have continuous outcomes of income, something like income, what is actually random when we carry out a survey, or in this conception of a survey, is whether an individual in our population or in our sampling frame it gets selected into our survey. We think about the income or the disease prevalence or whatever it is that we're asking in a survey as a fixed attribute of the sampling frame at the time of survey, right? But what is random, if we were to carry out the survey again, is not that some, person 101's income would change if we carried out the survey again at the exact same time. But what is random is whether or not we get to observe person 101's income, okay? So if we want to get estimates of parameters, or, anything that describes our population of interest, when we carry out a survey, much like other statistics, like frequentist statistics, we need a good estimator, and we're going to have to choose from the one that is most like our data. If your population is really large and your sample is really small, it may not be the worst thing to assume that your data arise from flipping a coin, right? That you have an infinitely repeatable experiment. This is, I think, most easily thought about in the context of like disease incidence. If we want to know a disease that someone doesn't recover from, say, if we want to know the prevalence of some binary indicator at a point in time, and we have a really large population and a small sample size, it's almost like there's an infinite number of people, and there's some being up in the sky, say, or wherever, who's flipping the coin for whatever outcome we're we're interested in, and each person is getting assigned a 1 or a 0 for that outcome based on this magical coin that could be flipped forever. That is sort of the philosophy behind all of the other statistics you've ever probably learned, right? You learned how to do a t-test, how to take the maximum likelihood estimate of something, etc. We're operating in this, what we call maybe a superpopulation framework, where we're sort of hypothesizing that time would run over and over and over again, get us to this point, and determine how many people have said disease. So the smaller your sampling frame or the population that you're interested in learning about, or the larger proportion of your population that your sample makes up, the more important it is to think about an outcome as drawing from an urn, from this finite population perspective. And we're going to talk a bit more about that here. So more formally, if we have a binary outcome, yi, that equals 1 when we have a successful trial, that might be, in the case of flipping a coin, getting a heads, and 0 when we have a failure, getting a tails. So if this is some binary, disease indicator, 1 would be disease presence, 0 would be disease absence for each of the little n people in our sample. In a superpopulation framework, and this idea that we have an experiment getting this disease or not, is coming from a superpopulation framework, an infinitely repeatable experiment, we might treat it as a Bernoulli or a coin flip. And then we would know that the mean of y of this random variable, the expected value for all people, or the expected proportion of all people who would have this disease, is just p, right? And the parameters for a Bernoulli variance are that proportion times 1 minus that proportion. In the finite population framework, which is this drawing from an urn framework that only has capital N number of possible iterations of this experiment, right? Things look a little different. Our expectation here, this is called the hypergeometric distribution. And in a hypergeometric distribution, we have large N marbles in a bucket. Large K of those are successes, whatever y indicates y equals 1. So we could call them red, if we have 2 colors. And then little n is still the number of marbles that we're going to draw without replacement from that bucket. Here, the expected value of y, or the proportion of little n marbles that we draw that would be red or have whatever a binary indicator attribute is big K over big N, right? The original number in the population of people, the proportion, of people in the population that have whatever attribute of interest that we're interested in. That is basically P, right? In a superpopulation framework, this is the population, or the probability of getting a heads in one trial. This is the probability of drawing a marble that's red with one draw from the bucket. The variance here is also very similar to the Bernoulli variance. We have P times 1 minus P, right, in our product. But we have this extra term that we call the finite population correction. This term is 1 minus little n, the size of your sample, over big N, the size of your population. If big N is small, this is larger and closer to 1. Or if little n is very close to big N, regardless of how big large N is, this is very close to 1, and then this term is closer to 0, right? So in that case, when we sample most of the population, when our sample gets to see a good proportion of it, our variance, our mean stays the same for any estimate we're going to do around prevalence, but our variance around that mean estimate is going to start shrinking, right? As this multiplier becomes closer to 0. If little n is small and big N is very large, then this looks more like 1, and this variance is basically a Bernoulli. So if you had a case where little n over big N is very small, maybe you don't need to do everything that we're going to talk about today. Maybe just going on with general linear regression that you know about and doing logistic regression is fine. However, the more proportion of the population you sample, the more sure you become of your estimator in a finite population setting. If this proportion is large, you're really doing yourself a disservice by modeling things as a Bernoulli because you're overestimating the variance of your estimate of prevalence. Okay. Now, there is something here that we need to talk about, which is how do we interpret p hat if that was to be our estimator in each case. In a Bernoulli, what that parameter means is if I were to flip another coin, what is the chance that coin would be heads? In the context of, say, disease prevalence, that would say something like, if I were to repeat all of human history and sample someone else today, carry out this experiment today, redo the sample or whatever, or maybe you're thinking if there were a million, a ton more people born and they had the exact same mortality, et cetera, conditions up to some point, then this is the chance we would expect for that new hypothetical person being born to get this disease. Or we might frame the results from a Bernoulli analysis or a typical frequent analysis, something like, what if we had a hypothetical large population? Even if our population is small, what if in this hypothetical world that we're thinking about as we're doing modeling, we have 1 million people in our population or 10 million or whatever it is. Here's how many we would expect to have that disease. In finite population, and so another way to talk about that before I go on to this might be to use the word risk. It is the risk. We're trying to estimate this underlying risk of whether someone under the similar circumstances or someone in our population, if we were to carry out another simple random sample or whatever it is, that they would get the disease. In the finite population case, this estimate of prevalence is really an estimate of prevalence in a population at a time and place. We're saying, what was the prevalence in Washington state at the date of the survey, right? So from this finite population perspective, we're sort of estimating a different thing altogether. We're estimating one realization, if you will, of a population under a Bernoulli process. So that's kind of philosophically why, how people might think about these differently and why survey statistics are different from other frequentist statistics. Mathematically, you can see that we would lose something by not acknowledging the finite population in many cases when this term is not close to 1. So we're going to go on and compare a little bit more about how we would estimate these things, and then dig into in both the Bernoulli or superpopulation case and the finite population case or the hypergeometric case, and then go on to survey statistics. So if we have little n observations yi, remember these are 0 or 1s, we've just got a binary indicator. This is sort of the normal assumption we have in regular frequentist statistics. We might estimate that prevalence or that risk, actually, the underlying risk of getting a disease as just the average of these things. And then we know the kind of canonical variance estimator is p hat times 1 minus p hat divided by n. On the other hand, in the hypergeometric setting, we would estimate p hat the same. Our variance estimator is still going to plug in that estimate of p hat into the variance, but we're going to multiply by this, right? So our point estimates would always be the same. The variance of p hat will always, in the hypergeometric case, will always be smaller than in the Bernoulli case, but whether it is impactfully different is another story. and depends on the size of your sample and your sample design. So the first sampling design that we're going to talk about today is what we call simple random sampling. When we do simple random sampling in the case of regular statistics, right? That's usually what we're assuming when we assume an IID sample. And we can sort of get away with assuming that in a lot of data cases if in small n, the sample size is much, much, much smaller than big N. But it's really not how we feasibly observe things about people, and certainly usually not how we observe demographic information. It's really hard to carry out a survey that's a simple random sample and get enough respondents or have enough resources to sample enough respondents to learn what you need to know about your population. We might also think about a simple random sample without replacement. That's what I've been talking about in the bucket context, right? I'm going to sample little N marbles from the bucket, and every time I take one out, I'm not going to put it back in. If we have simple random sampling and we don't know without replacement, we're doing coin flips or we're drawing marbles, but every time we draw a marble out, we're writing the color down and putting that marble back in. We're going to talk about some notation that you'll see in a lot of survey books, textbooks, etc. When we are doing survey statistics in this finite population sense, as I mentioned before, what's really random is not the attributes of the subject in the population. We sort of want to pretend those are fixed in time, or pretend that we could pause time and carry out a survey all at once. That's sort of the idea of a survey, right? We want to know about everyone all at once. We want the snapshot of a population. What's random is how we pick the sample. And if we were to pick the sample a second time, we would get different people in our in our response. So to account for that randomness, we need to know then facts about the chance that each individual gets selected into our sample. Those are necessary to get estimates of totals or means or proportions. To understand the variance of that random process, we need to know the joint probability of any two individuals in the population being selected into the sample. So if we have subject K and we want to know the probability that subject K is included, that's what that little claw means, in sample S, we might denote that pi K, that's usually what people would call it, and that would just be 1 over big N, right? The probability that someone gets any marble gets in my sample, if every time I draw a marble, I put it back in the bucket, it's just 1 over the number of marbles in the bucket. Because I'm doing this with replacement, whether any one marble gets pulled into the sample in a draw and any other marble gets pulled into the sample in a draw is independent of one another, right? I'm always putting the marbles back in. So every time I draw a new marble, there's an equal chance for any marble to get selected. So because they're independent, I can calculate this as the probability that subject K is in sample S and the probability that subject K prime is in sample S, which is also just 1 over N. So we would call this pi K, K prime, and that would be the product of those probabilities. Under simple random sampling without replacement, when we have N observations, the probability that any one person makes it into the sample is N over N, right? You can imagine taking all N of them out at once. And the probability that any two are going to be selected is the probability that any one is selected from the bucket of big N marbles. And then the probability that any N minus 1 are selected out of the remainder big N minus 1. Okay. So we're going to turn to R now. Has everyone been able to download the survey package? All right. So load the survey library. And then you're going to run this line data API, and we can real quick, yes. Yes.
Oh, I'm sorry. I got in late. I didn't get the package.
Oh, okay. Can you put your email in the chat
Yes.
and I will forward it to you. Anyone else who doesn't have the slides yet, just let me know. Thank you. Of
Thank you.
course. Okay. So, if you load, if you run this data API line, you're going to load a data set on academic performance of schools in California. I think the years are like 1999 or 1990 and 2000. We can check in a minute. If you run this question mark API line, you'll find the documentation for this data set, which will describe a bunch of things about it. We'll look at that in a second. And then we're about to use this survey design function. So I'm going to stop my screen share real quick and share my R screen so we can look at that documentation together. All right, so I'm going to load this library. Not like that. And then I'm going to load this data. And when you do that, you should see a bunch of data sets loaded. The one that's called API pop is the sampling frame. It's the population from which all of these other simulated sample data sets come from. This one is a simple random sample, a stratified sample, and then a 1- and 2-stage cluster design. One thing that's really nice about Thomas Lumley's book and a lot of the help pages and examples for this package is that they make use of these simulated data sets so that everyone can get the exact same results and know that they're doing something correctly. They're also really nice teaching tools. So if we want to see the documentation for the API data real quick, one thing that's really important when you're working with survey data is to read documentation. You cannot correctly analyze survey data unless you know how the data was sampled. So here we find that we have a unique identifier for each school. We know whether the school is an elementary, middle, or high school with this S-type variable. We've got names and numbers and district names and county names. We have the percentage of students who are tested. We have the academic performance index in 1999 and 2000. We have the target for the change between the 2 years, the actual change, some indicators of whether the school met certain targets, whether they're eligible for certain awards programs or subsidized meals, the percentage of English language learners, etc. And if we were to look at API SRS, we don't really need to have much explanation there, but this is a simple random sample, right? So it's just going to be sampling how many ever This is 200 schools from this list of 6,194. But when we get into the stratified and the cluster samples, we need to know what's the stratifying variable and what the cluster variable is. In the strat variable, we see here in the details and the descriptions here that it's stratified by school type, elementary, middle, and high school. And then it looks like in the two-stage cluster sample, we sample schools within districts. So the first stage of clustering would be the district variable. And we see an important note that there's an error in one of these data sets. Okay, so I just want you to know that that's what we're loading and know how to look this information up later about the data if you want to revisit these slides. And then the first and most important function in the survey package is the survey design function. You have to tell the survey package before you do anything, how was my data sampled? And so the first argument, the IDs argument, is always going to be a formula, much like a lot of things in the survey package. They love to use formulas. So remember in R, if you've ever done linear regression in R or something, a formula is something that has a tilde in it, and there's a left and a right side to the formula. In this IDs function or argument here for the survey design, we need to specify what the clustering scheme is. If there are no clusters in your data, you can either put a tilde 0 or a tilde 1. Otherwise, you want to put the names of the clustering variables in your data separated by plus signs in order of their nesting. If you have sampling probabilities, which we probably usually don't, usually we have weights, you would put those there. You would put a tilde in the name of the column vector. For strata, as we'll see in a bit, we'll also specify those using a tilde and the name of the columns that define the strata. You can pass the sampling weights. If you have information on the finite population correction, you would pass that. It's pretty rare that we do, but we will look at an example where we do. And then here, the nest argument is important. If you have stratified and clustered data, this would imply that your clusters are nested within your strata. If you don't turn this argument on, they might assume the opposite, which could really interpret and damage the way you're processing your data. Okay, I'm going to stop sharing my R screen and try to stay on the slides, but if anyone has a question where we need to go through exactly how this works in R, please don't hesitate to ask and we'll go back to that screen. Okay. All right. So we're going to start looking at simple random samples. So we're going to look at the AP-SRS data set. We have a column called the sampling weight. It's called PW. We have the finite population correction. For a simple random sample, the only thing we need to calculate that finite population correction, that 1 minus little n over big N, is the sample size, which is just going to be the number of rows in the data set that we have. And we need to tell R or survey somehow what the total population size is. So there's a column in this data set, API-SRS, called FPC, that contains the population size. Here I'm doing a cross table between the sampling weight and the finite population correction. Notice the finite population correction is the sample size, so that's the population size, so that's 6,194. If you divide that number by 200, you get the unique weight that all 200 rows in this data set have. Weights, which we haven't quite defined here, are taken to be 1 over the probability. So usually we're working in this setting, right? If there's a little n over big N chance that any individual makes it into our simple random sample, one might hypothesize that each response from these individuals represents big N over little n individuals in the population. right? So what these weights are saying in the simple random sample is that each response from these 200 people represents 30.97 people in the full population, because there's 6,001, or schools rather, in the population, because there's 6,194 of them, okay? In a simple random sample, we can see that we have the same weight for every observation, or every school, but I want to point out the uneven distribution of school types. If we just select a simple random sample, we get many more elementary schools into our sample, because in the population, there are many more elementary schools, right? Elementary schools tend to be smaller and have fewer students, so there are more of them. So if we want to specify the simple random sample design in the survey package, in this API SRS data set, I don't have any clusters, right? This is just a simple random sample. So I have to specify a ~1 or a ~0. There's no strata, so I don't need to specify anything there. I do need to pass the weights, and I am going to pass the column that has the finite population correction, or the population size, and then the data set. So one thing that I really love about the survey package is that it tells you in English what you just told it in code. So if you create that object and then go to your console and type in the name of that object and print it out, it will tell you that we have an independent sampling design. You'll see as we go on that it will communicate that we have different types of sampling designs based on different specifications. Systematic sampling is something that is very common in practice, but is not really ideal, I would say, from a mathematical perspective. Systematic sampling is a form of sampling where you would select every rth sampling unit from the sampling frame or list of items or subjects or whatever in your population. So if I have my list, like say I have a phone list of people in my population, I could pick R to be 8, let's say, then I would take the 8th person, the 16th person, the 30 or the 24th, 32nd, etc., as my sample. In this context, what is pi of k, or the probability that individual k gets into the sample if k is equal to r, or 8 in this example? What's the probability that the 8th individual gets into the sample? Anyone? If every time I take a sample from this list, I always take the 8th person, then what's the chance that the 8th person is in my sample? You can put it in the chat. You don't have to come off mic. Anyone? It's 1. They're always going to get selected. And person 9, 8 plus 1, the chance that they're going to get selected, pi of k for person 9, is always 0. This is a problem when it comes to survey statistics. There are some rules about the pi k's for things to be a real probability sample, where we can write out the mean and the variance and really understand the chances that each individual or pair of individuals is selected into a sample. And one of those rules is that the pi of k has to be above 0 for everyone. Okay. The reason people do systematic samples is because it's easy, right? If you have a really big list, you don't have to randomize, but also because in practice, many surveys are household surveys, and sampling frames at the household level don't usually look like lists. They usually look like maps, right? And someone might need to actually go through a selected block or village or whatever is being selected and fully enumerate with their eyes what are the available households, and then select from them for the sample. So like the demographic and health surveys, for instance, they use systematic sampling, but on a visual map of a selected area. So just a nerdy math question here. Can a systematic sample be implemented so that it's the equivalent of a simple random sample? The answer is yes. pi. Yes, y at 0 and 1. So in systematic sampling, which is just a way of drawing people or a sample from a population, much like simple random sampling with or without replacement, but you select every rth thing in your list. So if we have a list of people, like I said, and R was 8, we would select the 8th person, the 16th person, the 24th person, the 32nd person, and so on. So pi of k, the probability for individual 9, pi 9, would always be, sorry, pi 8 for individual 8 would always be 1 because they're always going to be selected into the sample. For pi 1, 2, 3, 4, 5, 6, 7, and pi 9, 10, 11, 12, 13, 14, 15, they're always going to be 0. Those people are never going to get selected for my survey based on this systematic sampling system. And we can't calculate certain things like variances if any of the in the probability in survey sampling, if any pi k is 0. We also can't estimate actually our point estimates because the weights that we use, right, are 1 over that probability. You can't divide by 0. So we're limited in that sense. So a systematic sample is something that happens a lot in practice and the way people carry out samples, but is actually undesirable from a statistical perspective because of that fact that all of our statistics and math that allow us to get variance estimates and good point estimates break down if there's a chance that certain people in the population cannot make it into the sample. However, people can do something like randomize our list of names, right? If we shuffle the list and then we always take the 8th person, we're basically doing an actual simple random sample. And in that case, we could actually calculate pi of k and pi of k prime and pi of r and pi of r plus 1. And it would look just like sampling without replacement. There's also a way to do systematic sampling by just going through every fixed unit on the list and not randomizing, but going through the list multiple times and randomizing where you start. So that's one way around the systematic sampling issue. Some people in practice might actually pick, say, 3 numbers between 1 and 25 at random, and then they'll take every, third and what's 25 plus 3, 28th, and so on. And they'll take every 10th and every 35th and so on. And they'll take every 15th and 40th. So that's a way to get around it. We're not going to talk about how to analyze systematic sampling data in the survey package. It's very complicated, but I do want to mention it because so many surveys actually carry it out for convenience sake. So I don't want you to be caught off guard if you encounter that. In practice, people tend to just ignore it and assume simple random sampling for calculations, but it's not ideal. Moving on to stratified simple random sampling. The next most simple design, besides a simple random sample, is to stratify the population into capital H groups, and then do a simple random sample within each of those groups. And from each of those groups, we would sample little n, little h individuals. In this case, the probability that an individual who is in strata H makes it into the sample is little nh over big NH, right? Within each strata, it's just like simple random sampling without replacement. So then the probability that any 2 subjects within the same strata are selected into the sample is little n over big N for that strata times n minus 1 over big N minus 1, just like sampling without replacement. For any 2 individuals that are in different strata, the joint probability that both individuals make it into our sample is the product of little nh over little nh prime. So why would someone do a stratified random sample instead of a simple random sample? Often this comes down to the availability of the sampling frame. So for instance, in the demographic and health surveys and the American Community Survey, well, at least in the demographic and health surveys, they stratify by urban, rural, and they stratify by state. And what they're sampling at the first level of their survey is something equivalent to like a US Census tract. American Community Survey does something similar, right? It's sampling within states, so it's certainly stratifying by states. And a lot of that is because certain things, like knowing census tracts or etc., or wanting to get at houses, you may not have a full list, right? And you can't enumerate, you can't just pop a list of all housing up to date out of thin air. So instead of trying to create a perfect sampling frame, you sample something larger. This is the motivation for cluster sampling, like these census tracts. And then, as I said, you would go around, find all of the active housing units and sample from them. So oftentimes we have stratified sampling because we have sampling frames based on each strata. Okay. And that might be how we get at the whole population. Another example would be the CDC's behavior risk factor surveillance surveillance system. That is stratified by cell phone and landline, because the sampling frame is trying to get at individuals in the US and it has long just been a phone survey. The landline list used to be relatively comprehensive for the population. As that's changed, the cell list is more comprehensive of the population, but we need to ensure that we're still reaching people who are only going to answer a landline. Also, for cost, convenience, and speed, this is one of the motivators for geographic stratified sampling, right? If I can make sure that I am going to sample a certain number in each state, and I know that I want that, if I try to do a simple random sample, first of all, I might not get enough people in each state, but also to do an actual survey requires usually sending people on the ground to do that, right? So if I can send people to fewer geographic locations, I can do that with less resources. Another motivation for doing the stratified random sampling would be if the strata sizes are different. This is particularly a motivator for the thing I just said about how a simple random sample may not get you things from every strata that you're interested in or enough observations. If the outcome of interest varies across strata, and in particular is rare within some strata, then we would want to oversample within that strata. And then if we know that our strata are related to our outcome of interest, we're always going to get a more precise estimator of the prevalence or the population mean or the population total than we would with a simple random sample. Okay. And those precision gains increase as that correlation between our outcome of interest and our strata variable increases. If we ignore stratification in our analysis and it's in our data, we might waste a lot of people's money, right? There might have been some very good reasons for why these strata were chosen. It makes an implicit assumption that the outcome of interest doesn't differ by strata, which may or may not be true. It obscures differences in the outcomes by strata. So if we don't a priori have a hunch or know about how the outcome would vary across strata, it's going to obscure those differences. We're going to overestimate our standard errors, which is like the worst statistical sin. Like no one wants to underestimate them, but overestimate them is sort of shooting yourself in the foot. And all of these things, as I said, worsen as the relationship between the outcome and the strata increases. It worsens as variability in outcomes across strata grows, and within strata shrinks. So that's basically saying the same thing in a different way. And then it worsens as variability in the weights grow. So if you have very different proportions of each strata being sampled and you don't account for this in your analysis, you're going to worsen some of the bias that we get in obscuring differences across strata and some of and the overestimation of variances or standard errors. So we're going to compare now the API SRS data set that we saw and the API strat data set, which is the stratified simple random sample where we've stratified by school type, the S type variable, which is elementary, middle, and high. And so I'm here just doing a crosstab between the weights for each school sampled into the API strat sample and their finite population corrections. So before we saw, sorry, these should say strat. We saw that the finite population correction for the API SRS data set was just the total number of schools in the API POP data set, right? The 6,100, whatever. When we do stratified sampling, each strata has its own finite population correction or own population size. And then, as we saw here, each strata is going to get its own weight. That's a function of the population size and the sample size within that strata. So here we can see the person weights across the rows. We have 50 with this weight that have this finite population correction. We have 50 with this weight and that total number of schools. And then we have 100 with this weight and that total number of schools. Okay, and you can see how this was calculated, the weight being 1 over the probability as the strata size divided by the sample size within that strata. Okay. If we want to look at the weights by school type now, we see that these weights of 15 belong to all of the high schools, the weights of 20 belong to all the middle schools, and the weights of elementary school, the 44 belong to all the elementary schools. To specify the survey design in the survey package, we still don't have clusters, so we're going to leave this as is, but we're going to add this strata argument. Again, a formula, so we use a tilde, and we're going to pass the strata variable to that. Okay, so that we're going to make this object called STR-SRS, so stratified simple random sample. And as I mentioned before, we get to then, once we specify it, put it in the console and have the survey package tell us what kind of design we specified. And indeed, it says we specified a stratified independent sampling design. So that's good confirmation that I did everything right and I'm ready to go estimate things with that data set. Okay. Cluster sampling is something that happens when we sample something, what we call primary sampling units, which are a collection of observation units. So if our observation units would be students, often, this is a classic case of cluster sampling, we might first sample schools and then classrooms. Right. And the motivation for doing this is usually because we don't have a sampling frame with all of the students on it. And because it would be expensive to do a simple random sample of a list of students, even if we had it, and send surveyors to every school to just interview like one student at each school, right? So notation, we usually would say we have capital C clusters. Like I said, we would call these clusters primary sampling units or PSUs. And in the population, we would have NC clusters. And still, we would use capital N without any subscripts to indicate the number of observation units. Individuals, we're going to index by K still. These are the observation units, and they're going to be contained within each cluster. So for one stage cluster sampling, we need to first calculate the probability that each primary sampling unit or cluster would get sampled. And then we can think about the probability that the individuals within the cluster get sampled. So the probability that PSUC is in our sample is just going to be the number of clusters that we sample, big C, over the number of clusters in the population, big NC. Right? We're sampling schools from a list of schools, say. In what we call one-stage cluster sampling, once we've sampled PSUC, we sample all individuals within that PSU. So here, the pi k within a cluster C that's in our sample is always 1 and it's 0 otherwise. This is still allowed, unlike the systematic sampling, because there's still a chance that every PSU could make it into the survey, even if once the PSU is selected or not selected, the individual probabilities of selection are fixed. What we refer to as two-stage cluster sampling is usually when we select the PSUs at the first stage and then we subsample within that. Okay, so instead of collecting or taking all of the individuals within each school or classroom that we select, we would further subsample individuals from there. In the DHS, we do two-stage cluster sampling. They call it, mostly the countries do two-stage cluster sampling, where the first level of clustering, the PSU, is the enumeration area or like the census tract. The second level of clustering, or the SSUs, the secondary sampling units, are households within a selected cluster. And then within every household, all women 15 to 49 are selected. Okay, so in that case, we have the probability of each enumeration area in a state and urban rural designation. Each one of those gets selected. And then there's the separate probability around if a cluster is selected, what's the probability that a household selected? And then in the DHS, at least, once a household is selected, the probability that every individual woman 15 to 49 is selected is 1. Okay. All right. So often when we're doing cluster sampling, it is out of necessity due to not having a sampling frame of our observation units, and or convenience, that it would be way too costly and inefficient to sample at the observational level or the observation unit level. Often these clusters tend to be geographic, but that's not always the case. When the size of clusters varies a lot within the population, so this could be schools, right? The schools in urban areas might be much larger than rural areas, even within an elementary, middle, or high school type. Or these might be actual geographic boundaries of like cities or census tracts or counties or something. And so often when that's the case, the actual way the cluster sampling is carried out is in what we call probability proportional to size sampling. And the reason for doing this is if you think about having, like, what if you had a list of metropolitan areas and you had a lot of money, you want to carry out a survey and you wanted to sample 10 of them? Well, what if you do that from the list of census metropolitan areas in the US and you don't get Chicago, New York, and LA in there? At least one of them, if not all of them. That might be a problem, right? Because if you don't, you've cut out our 3 largest cities and metropolitan areas, and maybe all of the other ones are different in some way from these really large ones. So if you make the cluster proportional to the size, as in the number of observational units within that cluster, you're more likely to sample large clusters. And even at some scales, it's almost like a probability of 1 that you'll always sample some of the largest clusters. And then for the smaller ones, you're going to sample, just a subset of them. If we ignore clustering in our sample, we are going to always underestimate our standard errors. This is because the number of observations from a clustered sample, all things equal, is not containing the same amount of information as a strata or a simple random sample of the same size where we've independently selected everyone. It's quite likely that the observation units within the clusters will have outcomes that are correlated to one another. This underestimation of the variance is going to be worse the higher that correlation amongst responses within a cluster is for observation units. So we're going to look at the one-stage cluster data set from the package, the API +1. And remember our clusters are districts. So I'm going to specify for the first time in the IDs argument, an argument with a column name instead of a 1 because we have a cluster. And that's going to be the DNUM column, the district number. The weights are still the PW column. We have finite population correction here. This is going to be the number of clusters, right? Not the number of individuals that we're correcting for now. And then of course, if we specify this and then print it out, we get told, yay, we did it right. We have a 1-level cluster sampling design. And it even tells us that we have 15 clusters that we sampled in our data. For the 2-cluster design, we're told that the clusters are first districts and then schools. And so just within districts, so we would specify this clustering in the order of the nesting of the sampling unit. So your primary sampling unit plus your secondary sampling unit. And then if we have, and you would do the same thing too, if you have multiple levels of stratification, you would just use a plus sign to specify that. And then if we have the finite population corrections for both of these level of clustering, the number of districts at the primary level and the number of schools, that one is going to change for every district, right? That's going to be the number of schools that could have been selected from that district. So we would also specify that by a plus sign in the same order as the IDs are before. And again, here we can put this in and then we get told, yay, we specified it right. It's a 2-level cluster sampling design with 40 primary sampling units and 126 secondary sampling units. Okay, there are more complex surveys even beyond this. Multi-stage sampling is often what we refer to as stratified cluster sampling, something that has a combination of those two things. One example is the DHS, the American Community Survey, is also a multi-stage sample and a multi-phase sample. We'll talk about that in a second. So this example that I've talked about already with the DHS is a stratified 2-stage cluster sampling. Within strata, we select primary sampling units. Within primary sampling units, we select secondary sampling units. And then within secondary sampling units, we select all observation units. As I mentioned to begin with, we need to tell our or the survey design whether our clusters are nested within our strata if we have this type of sampling setup. I could imagine one like a survey design where you would have multiple levels of stratification or clustering and some level of stratification would happen within clusters, but I've never encountered it in practice. But maybe it's out there. Multi-phase sampling is a really bad name. Well, these are 2 bad names. Statisticians love to give different things that have very different meanings statistically, names that have very close meanings or connotations in English. Multi-phase sampling simply means that you try to reach non-respondents. So if you send out you select a first stage of samples, you find some way to contact and attempt to interview your subjects. If there is large non-response, you might subsample from the non-respondents and try to reach those again. And that would be another level of randomness that would need to be adjusted for in the final analysis and survey weights. This is just I don't actually know how many of the YRBS things are up right now. They might be down. I know that the YRBS was removed late last week from the CDC's website, but as I mentioned before, it's super important that you read about the survey design of any survey you're going to analyze. And that might take a while, and you usually have to go digging. And so I just wanted to point out here where I would find the information I need to analyze DHS or YRBS or ACS data here. Just some common surveys. Okay, so we've talked about specifying the survey design in the survey package. We've talked about some canonical survey designs and why one would use one or the other and the consequences of not accounting for the survey design and analysis. And so now we're going to talk about estimation of important parameters with survey data that account for the design. So we've talked a lot about these pi k's. We've seen now some sampling weights. Normally, notation wise, we might call those WK. It's just equal to 1 over pi k. So if the probability of an individual making it into our sample is small, the weight is going to be larger for that person. If the chance that they get in there is big, their weight's going to be smaller, and they're going to represent fewer people in the population at large. In absence of non-response, which is pretty rare, WKs can sort of be interpreted as the number of individuals in the finite population that that individual's response represents, as I said. So in regular statistics, we might take the maximum likelihood estimator of P in a binomial random variable or under binomial assumptions to just be the average, right? We're going to add up all of the YKs, ones or zeros, and divide by the number of trials we had. The Horvitz-Thompson estimator is what we call a design-based estimator that's designed to calculate an estimate of a population mean for a survey sample. So the way the Horvitz-Thompson or sometimes Hayek estimator is calculated, sometimes called the Hayek estimator, is to weight each individual's response in the numerator. So I'm going to multiply all of the ones by their weights and the zeros by their weights. And then in the denominator, I don't want to divide by little n. I want to divide by all of the people, the total number of people that these responses represent. If I weight everyone's response by the number of people in the population that are supposedly like that person, right? Then I need to divide by the population total. If we have a simple random sample, these WKs are big N over little n, right? So since these are constant regardless of what K is, I can pull out, we can look at either side here. I can pull out N over N from each sum, right? And then I have the sum of WK up here. And then I have the sum of 1 N times, which is just N, right? If I add up 1 5 times, I get 5. I add up 1 little N times, I get N. So I am going to pull this guy in the numerator out front, and then in the denominator, I still have my N over N, and then my sum becomes N. Well, those guys are going to cancel, right? This little N and that big N, which is going to leave me with the big N over little n out here and a big N here. Those are going to cancel, and I get the arithmetic mean. So under a simple random sample, the thing we do with a survey, in the survey statistics context, or what we call a design-based estimator, a weighted estimator, the Horvitz-Thompson estimator, is exactly equivalent to the maximum likelihood estimator for a binomial probability. Under different designs, this link is not the case, but we still use this weighting idea or the Horvitz-Thompson estimator to estimate things in survey statistics. So you've probably heard of a weighted average before. If all of the WKs, or, if we have this sum of weights times responses, if all of these were between 0 and 1 and they summed up to 1, then these weights, this would be what we call a weighted average, right? Which is something we're all pretty familiar with, right? You probably have that form of grading system for any class that you've taken, okay? In this case, our weights, usually in the surveys, our weights are not between 0 and 1. So it's not really a weighted average, it's a weighted sum. But I just want to connect that back to a weighted average as sort of a motivation as to why someone might do this. So as I mentioned before, and kind of a high level, when we're doing finite population statistics or survey statistics, we're considering a finite population of size n, and we don't consider the attributes of individuals in that population to be random. We consider them to be p or fixed. So if we have yk here in a population of size n, we want to take a little sample of size little n, all the yks are fixed. What is random, or what we usually denote as random, is this random variable called zk. That's a binary indicator of whether individual k made it into our sample or not. So what we're actually computing the expectation of when we think, when we get our observed data little yk, is the product of big yk, the fixed true attribute about that person, and their value of zk, which is random in every sample. So the expectation of this, yk here is a constant, right? It's not random in this context. That can just be pulled out of the expectation. And then the expectation of this Bernoulli random variable is got to be pi k, the probability that zk equals 1, right? So the expected value of yk, or of this random variable that we're interested in the finite population, is the person's true value times their probability of getting into your sample. Right, that's what's random. Whereas in the superpopulation context, or like a Bernoulli logistic regression context, the expected value of yk would just be p, just the probability that that event occurs, the probability that yk, when yk is random, is 1. So there are two different sources of randomness. So the first target of inference, or typical population parameter that comes up in survey statistics, is the population total. This might be the total number of people with a certain binary attribute, right, where yk equals 1, or it might be something like the total income, or the total crop yield, or something from a survey of crop plots. So in the population at large, the true population total is capital T, right? And that's the sum over all big N individuals of their YK response. We are usually trying to estimate this capital T, so we're going to put a hat on it. T hat is then the sum over our sample of the weight times the response for each of our little n individuals. Put another way, this is the sum of their observations divided by their probability of being included in the survey. If we know the probability of each individual making it into the sample, and the probability of each pair of individuals making it into the sample, then we could estimate the variance of T hat with this expression. We would take the product, we would sum over each pair of responses. K equals 1 to n, K prime equals 1 to n, of the product of their responses divided by the product of their individual probabilities of making it into the survey, minus the product of their responses over their joint probability. So this is a lot like, if you remember probability class, that the expectation of, or the variance of a random variable is the expectation of x squared minus the expectation of x squared. This is a similar setup. Quite often, when we work with public survey data, we are not given anything related to this joint deal here. We have our weights, which are related to the individual pi k's, but we don't have joint inclusion probabilities. If we have stratified samples, then we would want to get the estimate of the population total by estimating each strata total individually and then summing up those estimators. So we would sum over each strata, and then each individual in our sample within strata, their weight times their response, and the variance would work the same, except these pi's now are going to vary by strata, not just by individual. All right. And then, of course, strata are mutually exclusive from one another. So the variance of T hat is just the sum of the variances for each strata's total. There's no covariance between any two strata. In cluster sampling, we do the same thing. If we want to estimate the total for the population, we're going to know that that is the total of the sum of all the totals in every cluster in the population. And then we could estimate that by adding up in our sample the clusters that we have and the individuals within the cluster of their weight times their response. In a cluster variance term, we are actually subtracting out here. I didn't put this here, but this variance depends only upon individuals in the same cluster. So we're subtracting same thing with the strata, but we're subtracting each individual's observation in the sum of squares, where we estimate the variance from the cluster or strata level mean instead of the overall mean. Really unnecessary. We're going to keep going, but the same principle holds even when things get really complicated. We're going to sum, if we have clusters within strata, we're going to sum over strata, and then primary sampling units within each strata, and then secondary sampling units within each primary sampling unit, and then observation units. Luckily, you don't have to do any of this by hand. There is a survey total function in R. And so once we've specified those designs that we specified for each survey design before, the SRS, the stratified simple random sample, and the 2 cluster, we can use this survey total, SVY total function, to estimate the total enrollment. So I'm going to pass a formula to the first argument of this survey total function, who is going to be a tilde, and then the name of the column I want to estimate the population total for. And then I have to specify the design object. If you don't specify an NA.rm equals true, if there are observations with missing values of the outcome that you're estimating, you will get an NA as a result. So I put that here because it's only in this one that we have that case. Okay, so we have 3 estimates here from 3 different samples from our API POP data frame, sampling frame. Let's compare the totals. This total is much higher. These 2 totals are pretty similar, but much higher than the 2 cluster design. The variance of these 2 are much lower than the variance of the cluster design, which is expected. And the stratified standard error is quite a bit smaller than the simple random sample, which we would expect because we would expect enrollment to be related to the strata we know were used for the sample, which is school type. Enrollment size is different for elementary, middle, and high school. So we're going to see that precision gain that we talked about for conducting a stratified simple random sample instead of just a simple random sample. To estimate a mean, we can use those estimates of population totals in the numerator, but we also need something in the denominator. So the population parameter we're estimating here is what we call big Y bar, and that's going to be the sum over everyone's, remember these are fixed values of the outcome in the population, divided by the total number of people in the population. Y bar hat is what the survey world calls the estimator of this population mean. And that's going to be the weighted sum of the responses divided by the known population total. We can do this in these example data sets that we're working with because we have the sampling frame and we know what these finite population corrections are. In practice, you might not know that. And we're going to need to estimate this big N2, which we kind of did. I already sneak peeked this for you here. We're going to do usually by summing up the weights. Okay, and then here I want to point out that the variance of Y bar hat, this should look familiar, to most of you. If you've ever done from a frequentist point of view, the variance or the standard error for X bar, right? It's going to be the variance of T here divided by N squared. And just like what we talked about at the very beginning of this lecture, how there was the finite population correction on the binomial or the hypergeometric variance of a random variable, we see that under a simple random sample, we would also have a finite population correction on the variance of the population mean. That also is going to decrease that variance as we see more and more of the population, eventually to where if we were to see the whole population, right, there would be no variance. We would have observed the truth. But otherwise, this looks just like the standard error that we would use to estimate for just a regular simple random sample mean times that finite population correction. There's a survey mean function. And so if we wanted to know the mean enrollment per school, just before this, we estimated the total enrollment for this school. We see that we have higher estimates again for the simple random sample and the stratified simple random sample than we do for the two-stage cluster. We have much smaller standard errors in the simple random sample and stratified design than we do in the two-stage cluster, as expected. And again, we see that we have a much more precise estimate in the stratified design than the simple random sample. To estimate proportions, we've kind of already walked through this in the hypergeometric sense, but to put it in the notation for survey statistics, the real population parameter we're after is big P, and that's the sum over every individual in the population's outcome YK, which is binary. And then we would divide by the total size of the population. And then just like in standard statistics, we might estimate the variance this way of p hat times 1 minus p hat over n. And if we had information on the finite population correction, as we talked about at the beginning, we would multiply that here. The survey mean function is how you would still calculate the estimator, the point estimate for a proportion in the survey package. But if you want the proper binomial, like corrected standard errors and confidence intervals, then you will need to use the survey CI prop function. So confint is a function that is just in R. You may have used it before, and it can be used on a lot of objects to pull out confidence intervals. Here you see that for this binary variable, the 95% confidence interval is 0.76 to 0.868. And this is what it would be if we just treated it as a mean with the standard error that comes out from running this function inside of it. If we run survey CI prop, so this is for proportions, confidence interval proportion, we get a slightly different confidence interval. It's not really much different in practice, but this is technically more correct. And so you have to use this extra variable. So just something to note. In practice, it's usually not a huge difference. Here's another example with the stratified design, where if we don't use that, we get, again, a different confidence interval. We would say this one is more correct. In practice, they're not very different from one another. Okay, so what if we don't know the population size? Then we need to estimate in hat, and then we have a ratio of estimated things when we want to estimate Y bar hat. This is kind of a bad situation in statistics. It's not easy, even if those two variables, we know they're normal. It's kind of a pain, like we can do it, but it's really hard to know in many cases what the distribution of the ratio of two random variables looks like. So the survey package does this thing called Taylor linearization to estimate variances in this case where you don't pass a finite population correction variable to the survey package, and it has to estimate any population size using the sum of the weights of observations within that category. This is technically an example of what we call ratio estimation in survey statistics, which can be done not just when our ratio is an estimator of the population size on the bottom as it is when we're estimating Y bar hat here. In general, ratio estimation is a tool of survey statistics that is used when we have a survey to collect information on both Y and X. But we are probably interested in knowing something about the relationship between these things. But there is some external data source where X has been measured, and we have a pretty good idea of what the true population. There's a northern flicker in my window. It's a really big bird. Okay, it's gone. That was exciting. Okay, so this might be something like population size, as we are talking about here, but it might also be something like maybe income, which we know, like total state income filed, right? That might be something that we can look up in a known aggregated number in some publicly available data source. But at the individual level, we don't, or at the population level, we don't know anything about why. And then if we collect information about income in our survey, we can compare the estimated total income in our population from our survey to the real total income in our population that we observed somewhere else, right? If the ratio of those two numbers is very far from 1 and it's above 1, we would know that our survey is underestimating whatever that X variable is, say it's income. If it's very far below 1, we would be overestimating the total income. So if we assume that the over or underestimation of Y is in the same direction as the over or underestimation in X, then we might use this ratio to sort of inflate our estimate of Y based on what we know about how our survey estimates X as compared to the truth. Okay. So here is an example. We're going to go back to the survey mean, and we're going to estimate mean enrollment just for the simple random sample. But we're going to create a new survey design where we don't specify what the finite population correction is. So we're going to put ourselves in that situation where we don't know what big N is for the population. I'm going to remind you what the survey mean output is for the SRS DES, where we do specify the finite population correction, and then where we don't. The point estimates are exactly the same. Okay. But the standard error is slightly larger in this case because we are estimating technically N. In a simple random sample, it's worth noting that the sum of the weights is always big N. As our survey designs get more complicated, the sum of the weights is not an exact estimator of big N, and these differences will start to change. So here's for the stratified simple random sample. I'm again going to specify a no finite population correction design, and then I'm going to compare the results from the stratified design where we do have finite population corrections to that without. We get the same point estimate, but we get a slightly larger standard error in the case where we don't provide the finite population correction. Okay. The survey ratio, this is kind of stuck off. If we wanted to use the survey ratio function, which does ratio estimation of this general type, we can get the same results as what we did here, where because we simply did not pass a finite population correction in the survey design, the survey package knows, oh, we're going to need to estimate the denominator. Here, I'm going to first update my simple random sample design here with a new variable that's just a value of 1 for each individual. Okay. And then I am going to specify in the survey ratio the numerator. That is the Y here. So that's going to be enrollment. And then my denominator is going to be the variable that I have measured in my survey here. So that is going to be just this, are you included in the survey, which is 1 for everyone who was. And then I pass the design, and it's going to calculate the estimate of the enrollment that's weighted and the estimate of the denominator that's weighted, and then calculate the standard error using that Taylor linearization. So if I put in this argument, you can see I get out the exact same information as if I did the survey mean function without the finite population correction. So all of that to say, just to show you that this is ratio estimation, if you've heard of that, you need not go all the way through the kind of tedious process of specifying the survey ratio function when what you just want to do is estimate a mean and you don't have finite population corrections. I would save the use of this function for when that X variable in your ratio estimation is meaningful. For small area estimation, there's a really handy function called survey by, and it takes as its first argument, just like survey mean and survey total and survey CI prop, the variable that you want to estimate something about in the population, whether it's the total, the mean, or the proportion. And then its second argument is by, and it takes a formula over some categorical variable whose individual levels or subgroups of your sample we're going to get population estimates for. Then we pass the design object that we're going to use, and then we pass the function, the survey function that we want to use to estimate. So if I want to get the total enrollment for elementary, high school, and middle schools, I would specify this, right? Here you can see our total enrollment for elementary schools is higher, as we've expected and talked about before. The differences are not too big, I would say, between the point estimates for the see, this is stratified design and the simple random sample, but you can see that the variance is much smaller, especially for high school and middle school, when we account for stratification and do a stratified sample. There are also functions for general linear models. So it's SVY-GLM. The first argument is a formula, just like you would use with the regular GLM function. You need to pass your design object and the family argument like you would in a GLM. You can always use the Gaussian family to do just regular linear regression. What's happening when this is done in the survey weighted context is actually that we are weighting each observation's contribution to the likelihood, essentially, but the weights are being accounted for here. So here's the output of these two models where we take this binary outcome as a function. We regress that on the proportion of the school that are English language learners, the proportion who are eligible for free and subsidized meals, and the proportion of students that have moved recently. And the coefficients for the intercept change here. And some of the results, I mean, none of these really hold up, but the main thing I'd like to point you to is that in this case, the stratification really helped our precision. In this case, our coefficients are not being estimated more precisely by the stratified model. That would suggest that stratification is not very related to our outcome variable or to the relationship between our outcome variable and any of these other variables. Okay. If we don't have a probability survey, so all of this is when we have a really carefully carried out survey, what do we do? Or what if we wanted to do some sort of stratification, say on race or something, but we actually didn't have that in our sampling frame. We didn't have any way to do that. We might use post-stratification for that. There is a post-stratify function. And basically what this means is that you re-weight all of the weights in your data according to the frequency of by some category, some post strata you're going to specify, like race and ethnicity. You re-weight the weights so that the sum of the weights gives proportions or totals that mimic those in the real population, which you have provided from some population level data. So here I'm getting the total number of school types in the population, And then I'm post-stratifying my simple random sample on school type. Remember, I didn't stratify by school, and I'm doing that by passing the real distribution to that. So we're not going to talk more about that, but it's a really common thing that happens and that people ask in this workshop. And so this is, if you want to talk more about post-stratification, perhaps we could set a meeting. But there are some ways of still being able to analyze data that come from surveys that are not probability surveys. In the survey package, there's also a handful of functions for visualizing your survey data that account for the survey design. There's an SVY hist function, an SVY box plot function, a plot function, a conditional plot function, etc. So we're going to go through some of these examples. If you're a tidyverse person, this may feel a little weird. This is all based on base R. So it works a lot like the hist function, if you're familiar with that. The first function here that I'm running is the survey hist function. I want to map the enrollment. I want this to come from my stratified simple random sample. I'm going to change the main title and the X label. I want to see frequency on the x-axis, not probability. I want the bars to be gray, and I don't want a border on my bars. I'm also going to add on here the estimates of enrollment by school from the two-stage cluster design. I'm going to make those navy, and this add equals true argument is going to add that histogram onto the one I've already drawn, and then I'm going to make a legend to identify the two colors. So this is the result here. And why this is different from just going and making a histogram is that what we're seeing here is actually frequencies determined by the weights. Okay, so the outcome for each school is just the enrollment it reported, but the height of the bars is determined by the sum of the weights that fall in that bin. Okay, so we're taking account for that upweighting and downweighting in the survey design when we look at the data visually. We can also do this comparing the stratified. Here I'm comparing the stratified to the simple random sample. Just another example. You can see that here. Survey plot works just like the plot function in base R, except it wants a formula here. This API data set was really about measuring this academic performance index in 2 years. So I'm going to plot the 2000 score against the 99 score, and I'm going to do this for the stratified design and for the two-class design. There's a style argument, and the style argument governs how the weights are going to be visualized in the data. And so here, when I say bubble, it's going to make the size of each dot weighted according to the sampling scheme. So here on this side, right, remember we have 3 strata. We have elementary, middle, and high school. There's only going to be 3 different sizes of bubbles. Here, when we have this 2-stage cluster design, we clustered by district and then schools. And so every district and every school within every district is going to have a different size bubble. As you see here. So it's really important, like if you didn't do this, right, you would just see all of these dots at the same size, but in the population, that's really your sample data. That is not describing what's happening in the finite population setting. There's also transparent. So in this case, it will emphasize the weights according to the transparency level of the dot that it draws. The things that we didn't cover in detail, post-stratification, I mentioned a little bit about this. Raking is like post-stratification, but say you wanted to post-stratify on age and sex, and you didn't have data on age intersected with sex, like you didn't know the number of 5-year-olds that were male, the number of 5-year-olds that were female. Instead, you had the number of individuals in your population by each age group, and you had another table that broke it down by sex. That would be called raking. We would do some sort of iterative procedure of post-stratification where we re-rate the weights so that the age distribution works, and then so that the sex distribution works, and then go back and forth until we kind of reach a happy medium. Replicate weights are a unique thing that are released when releasing parts of the survey design variables like we used in all of these examples, so specifying the strata and the clustering would actually probably be a violation of privacy or a risk for identification of individuals in the survey. And so in that case, so BRFIS is one that comes to mind. They release a ton of replicate weights, and there's a way to specify your survey design with a slightly different function called survey rep design. And it will take an argument that describes all columns that contain those weights. And then once you have that object created, you can use all the SVY functions we talked about with that object. We didn't talk about non-response very much. Usually any survey that you're going to be using that's already packaged as a product has accounted for non-response in the weights. If you have your own data, you'll need to make sure you adjust your sampling weights according to non-response rates. Multi-phase sampling is what I talked about, where you resample from the folks who didn't respond. We didn't cover how you would analyze that data. And then model-based estimation is what one might do when you have information on the clustering variables and the strata, but maybe you don't have weights, or maybe for whatever method that you're doing, there's not a way to do it in this survey package. For instance, if you want to fit a random effects model, that would be a case that you can't do in this survey model that isn't a cluster variable, right? You can account for clustering. Then you would simply put in, you wouldn't do a weighted analysis. You would put in fixed effects for all your strata and random effects for all your clusters, and go from there. This is extra. We don't really need to go through it. One time I did this talk and someone wanted to know how we would estimate the difference between two variables in a survey. So this is an example if you're interested in that, how we would go through that. But any questions?
I don't have any questions at this time, but they may come up the more
Yeah.
I dive into this.
Yeah, I hope these materials really are just there to help you when you're trying to sit down and analyze your data. You can kind of go back to these. And I really, survey t-test. Okay, I got a question for a survey t-test. I can't do an example on the fly, but I'd be happy to add one to the slides and send out an updated set of slides either tomorrow or Monday. It's going to be just like a t-test, but instead of like, so if you have a 2-sample t-test and we want to know, whether the difference in the sample mean between two groups is different from 0, say, our classic one. Instead of comparing the sample mean, it's going to compare that Horvitz-Thompson estimator. So it's going to get the weighted sum of all of the outcomes divided by the sum of the weights, and then the standard errors associated with that, and then calculate the t-statistic. But otherwise, it'll be doing the same thing. And so then what you're actually testing is the difference of means in the population, which is what we want to be doing. Yes, I will send out an email once the recording of the lecture has been posted on our YouTube channel, which will probably happen tomorrow.
So when I installed the survey, when I did the install, I noticed in the slides you have specified dependencies. I didn't specify that. Is that how important?
That's okay.
Okay.
That just means that if there's a dependency the package needs to run that you don't have, it's going to install it. It can actually be kind of a dangerous argument to specify if you work on shared computers or computing environments quite a bit. But as long as the package is loading for you and you didn't specify that, you should be good to go.
Great. Thank you.
Yeah, of course. All right. I'm going to stop recording. And like I said, I'll send out an updated slide deck with the survey t-test added, and I will send out a link to the recording when it's up. Take care.